Hello Year 9. Right, I'm going to go through the answers from yesterday and look at occasions when it appears that mass isn't being conserved. Okay, so your first slide, we did the first one together, so you add these two together because the total of the reactants must equal the total of the products. For B, you know what your total is of your products, so that's 117 with the 2 NaCl. So the missing reactant must be the difference between those two numbers, because 71 of that 117 is made of chlorine, and the remainder is made of sodium. Okay, so 117 minus 71 will give you 46. C is straightforward because you just add them together, so that gives you a total of 80. Now D, this one caught me out. Okay, so you have to look at where the arrow is. Now in this reaction, which is one that we'll talk about in a minute, calcium carbonate is one reactant and it's breaking down into 2 products. Okay, so you've got a total of the reactants of 100. 56 of that is one of the products, so the remainder is the other product. Okay, so 100 minus 56 will give you 44. Now the last one, E, you've got 2 reactants and 2 products. Okay, so you need to work out first the total of your reactants. So you'll add 40 and 36.5 together first, that will give you your total, and then you can use that to work out the mass of the missing water on the product side. Okay, so I've got 40 plus 36.5, and then I take away my 58.5, which gives me a total of water of 18. Okay, now if you notice, you will actually look at water, and if you calculated that in terms of its formula mass, you'd have 2 lots of 1 for hydrogen, okay, and 16. So it would still add up to 18 in terms of the mass of each of the atoms. So there's 2 ways of doing this. You can either work out the relative formula mass, or you can do it in terms of addition and subtraction. Okay, so it's one way of checking your answers, but they are related, okay, because water adds up to 18 with its formula mass. Right, okay, just in terms of yesterday, we said that reactions, the atoms get rearranged, but they're still there. So that's why the mass of the reactants is exactly the same as the mass of the products, because nothing's appeared, nothing's disappeared, everything just gets rearranged. And that's the same with it dissolving as well. Even though it's a physical change, it's not a chemical reaction, it still ends up with conservation of mass. Okay, so you'd have a solvent and a solute. The solvent is the liquid, the solute is the solid, and then you end up with a solution. So the masses are going to add up. Okay, now with copper sulfate, the blue powder here, it's quite straightforward to see that it's still there. Okay, because the solution is blue. Okay, you can tell it's dissolved because it's clear, you can see through it, but it is a blue solution. If it's something like salt or sugar, because it goes colourless again, then it appears as if it's disappeared. It looks as if it's disappeared, but it hasn't. It's still there hiding between the particles of water. So no mass is being lost, it's still there. That's why the maths part of it adds up. Okay, so if I have a mass of my liquid of 490 grams and I end up with 520 grams of solution, the missing mass must have come from my blue powder, my copper sulfate. So I do my simple subtraction, and then that will give me 30 grams. Okay, so they add up on the left hand side of the arrow to add up on the right. Sorry, on the left hand side adds up to the right hand side. There's no arrow in this one because it's not a chemical reaction. So just have a little go at those 2 questions just to get your head in gear. Right, now there are 2 occasions where it would look like mass is not being conserved, okay, and it's all to do with gases, right? So gases are the key. Now, you might have done this experiment before, if not, you will definitely do it in future. Now, we've burned magnesium in an open flame, and you've seen it burns really, really brightly, and it produces that white powder, okay? Now, when we do that, quite often the white powder falls onto the desk, and it all breaks up, and we can't scoop it all up. So this is what we do to try and calculate the masses that are involved. So this time I weigh my magnesium and I put it inside a crucible. It's those little pottery bowls that we use. You put it inside the crucible and you heat it until it reacts again. Now you need to just lift the lid off the crucible a little bit because it's reacting with oxygen and you need to let enough oxygen in. Now oxygen is a gas because it's in the air. It's going to join with the magnesium to make magnesium oxide, okay? And that's why, even though it's very, very tiny, there should be an increase in mass, okay? It looks like the mass has got bigger, but it hasn't. It's just that we don't weigh the oxygen beforehand because it's in the air. We can't say, all right, I've got a handful of oxygen that weighs a certain amount, okay? So in this case, because oxygen is joining to something and becoming a solid product, it looks as if the mass increases, okay? So the chemical reaction for this is magnesium plus oxygen will give you magnesium oxide, and I've got that here. Now that's an oxidation reaction, so any time that a gas joins with another element, it's going to look as if it's got heavier, okay? So if you look at the reaction equation at the bottom, this is a massive clue as to what's going on because they've included the state symbols. So in the brackets next to magnesium you've got an S, that stands for solid, okay, because magnesium is a metal. The oxygen is a gas, that means that you can't weigh it beforehand. Now because it's formed a solid product, that oxygen is now measurable, okay, so it is actually measurable. You can include that in the mass. So this is the clue that you're looking for, that the looks like the mass has got heavier, okay, the mass has increased. It hasn't, it's just that we couldn't weigh the gas to begin with, okay. Now this is another example. So you've got steel wool that you burn on like a balance, okay, so this bar here that's been set up, it's balanced, okay. So when I burn the steel wool again, it's going to combine with oxygen, okay, which is going to make it a little bit heavier, and it will tip the balance very, very slightly, but it's more visual. You can see it much more easily than the magnesium oxide because it doesn't always work. This one, you can see that the balance will tip because it's got ever so slightly heavier because that oxygen has been combined with it, okay. Now this is the opposite. This is where your gas is a product, okay. So you've got a little picture there showing you, I don't know, like vitamin C or Alka-Seltzer or something, where gas is being released. Now all of those bubbles will pop and the gas will more often than not escape, okay. So if gas is escaping, even though it's small amounts, it will cause a decrease in mass, okay. So in this case, this is often the setup that you have. You will have normally a solid and a liquid reaction mixture, so quite often it would be magnesium and acid, it could be calcium carbonate and acid, so like marble, little bits of marble that we've used. Now you put cotton wool in the top so that none of the reaction can escape, okay. If you've ever drunk a glass of really, really fizzy pop, when you drink it you can feel the bubbles popping and you get like a wet nose, okay, because some of that liquid will escape as the bubbles pop. So we don't want to lose liquid mass, we just want to lose the gas out of the reaction, and that can squeeze through the gaps in the cotton wool, okay. So what we would see on the balance is that as the gas is produced, you've got bubbles there, you always look for bubbles, that's a real clue in an exam question. The mass would look as if it is going down, but that's only because the gas is escaping. If we could catch that gas and weigh it, the mass would stay the same, like we've talked about, okay. So if you have calcium carbonate, which is the little bits of marble, so in this reaction if I use calcium carbonate it will be solid, you can work out how much gas has been produced using the equation, okay, which I don't have, but I have a general one. So in this case, if I've got calcium carbonate, I'm going to end up with calcium oxide and carbon dioxide. So I can know the mass of these two because they're both still solid, but because I've got gas here, again you'd look for that clue of gas, that's going to escape, so the mass will look as if it's got less, okay. You can work that out in the same way as you've done before using subtraction. So this is another carbonate, this is copper carbonate, so I'm going to show you how to do that. If I start off with 10 grams here, okay, the green powder is 10 grams. As I heat it, carbon dioxide is escaping, but the copper oxide stays as a solid. Now I can work out how much carbon dioxide has been made because I can use that subtraction. I've started at 10 grams and now I've got 6.2 grams. The difference is the carbon dioxide. Okay, so 10 minus 6.2 is 3.8 grams of carbon dioxide that's been produced. Okay, so again, like I've said, this is the copper carbonate example. You've got a solid to start with, a solid product, but that gas is a clue as to why the mass has decreased. So these state symbols are really, really important. Now your task on class charts, okay, is you've got a sheet where you have to explain what's going on in 3 reactions, similar to what you did the other day, using what I've taught you about today. And then there is an exam question just so that you can see how they might ask you about this idea, this concept, this topic in an exam. Okay, so that's your 2 tasks today because you had an easy day yesterday.